Well, Matthias, congratulations again on behalf of Kaggle. Great work in the March Mania competition in this iteration. We love hosting with Kaggle. We love seeing the different outcomes. We know that there's been some years where upsets wreck existing models, and some years where the same models from many years ago are the primary foundation for the winning models today. But we're excited to see how you did it. So I know you have a presentation prepared. Why don't you go ahead and walk through your presentation? I'll save some questions for the end, and we're excited to see what you did and how you came to your solution.
Cool. Well, and thanks to you all again. I know Kaggle hosted this, so it was my foray into Kaggle competitions, really. So I really appreciated the opportunity and the data. You know, I think most of us who have been doing this for a while know that sometimes just the biggest hurdle is getting the data, and you all provided just a big drop of it, so that was very helpful. So yeah, this is my March Mania 2023, how to almost win with these 5-ish tricks. And I'll even just skip ahead to the background. I am Matthias. I live here in Seattle. I'm a data scientist at Data Robot. You know, at night when the kids are in bed, I like to play with sports data. That's what I do. So some of my relevant prior experience includes running a soccer analytics website that I've run for about 10 years. So it seemed like, well, soccer is totally different than basketball, but actually there were at least 2 major decisions I made in my process that came from work that I've done predicting soccer outcomes. So I'll make sure to bring that up as they come up. But maybe most importantly, go ahead.
Does that make you a Sounders fan then?
No, I see, and that's about the worst question to ask. I'm from Oregon and grew up not too far from Portland. Yeah, you really can't be a Sounders fan. But here's the problem. My 2 daughters were both born in Seattle, and the older one said, well, I'm a Sounders fan because I was born in Seattle, and I can't make a super logical argument against that. So I might end up with a split house, you know, as they age.
That's great. Sorry, continue.
No, that was great. Jump in. I know Addison probably has lots of great questions. 2 of the more important pieces of information, I can make lands with both hands for sure, and I have a BA in Hispanic Studies. You know, so Pablo Neruda will help us, guide us through this presentation. Let's keep going here. So just a few of the high-level summary items that I'll dive into a little bit more. Some of the different training algorithms that I tried. It involved one of the tools that I used, which was, in addition to R and Python, I leveraged Data Robot. I'm a data scientist at Data Robot. So that is automated machine learning software that can help accelerate the process of building a lot of models and testing a lot of models and seeing what types come out. So some of the top models on the AutoML leaderboards included elastic nets, light gradient boosted machines, XGBoost, of course, and a Nystrom kernel SVM. And the ones that typically won, and I built multiple models. So the ones that typically won the competitions of models were elastic nets. And I think I have a theory on this, actually. I think with sports, you know, everyone wants to play 10-dimensional chess when they try to predict who's going to win a sports game. I mean, you've heard the hour-long conversations in the bar, right, when you're watching the game. And it's like, I don't think it's actually as complicated for sports as people want to make it out to be. I think there's a lot of very linear, very monotonic relationships in sports. If you're really good at something, you know, you're going to have a higher probability of winning. If you're really bad at something, you're going to have a lower probability of winning, and everything in between is a pretty straight line, right? Or at least in like the log odds space or whatever link function you're using. But I think it actually kind of made sense to me. Elastic nets came through. They're able to identify, you know, pretty well relationships that are fairly monotonic and one directional and linear. And so not super surprising. Some of the most important features, and I'll talk about some of these more at length. The conference strength I used as a strength of schedule. I think, you know, stepping away from my submission finished second, but I think in another year it could have finished 202nd or 2002nd, right? Like, I think the things to take away, at least that I tried to take away, were things that I think would work on average year over year, but maybe not every year, right? And conference strength, I think, was the way that I took into account that strength of schedule. And strength of schedule is so important in college basketball. It has one of the greatest, in many of the major sports, college basketball and many college sports have some of the greatest diversity of talent spread out across all 360, however many teams there are in college basketball Division I. And so you have to have something that controls for, some of these teams just weren't playing the best teams. And if they, averaged, like South Dakota State women averaged, I think, something like plus 27 point differential in conference, but they're in the Summit Conference, right? And the Summit Conference rarely competes with, the Pac-12 and the Big East and the SEC. And in fact, as I was kind of breaking down South Dakota State and during one of my iterations, I noticed that they lost by like 20 to the Pac-12's fifth best team, Washington State University. And they lost by 9 to the Big East's third best team, Creighton. And they slipped by the SEC's fifth best team, Mississippi State, I think, by 1. And it's like, yeah, they're beating the Summit Conference by 27 points a game and going 18-0. And that looks great to a model, but who are they playing? And so the way that I accounted for that was by looking at the team's conference strengths and then just training the model on roughly the last half of the conference schedule and then the tournament each year. So basically like your February and March games, essentially. Home indicator was important because I didn't just train on tournament games. And for that matter, the women's tournament does have home games. So there's always going to be home games in the training data set anyway. And I used a fair amount of February and March regular season games. So I had to make sure that when I had 2 teams on that line to predict, the home team and the away team, that I had an indicator that said the home team was truly a home team, or the indicator that said this was actually a neutral site game and don't pay any extra attention to that home team, right? So the home indicator became pretty important. And then some of the actual basketball statistics that came through had to do with offensive rebounding, free throws, point differentials, and for that matter, field goals and 3-point field goals made differentials and things like that. And I think I've got some plots to kind of dive into that a little more. I used a variety of tools. I went through my master's program, and R was very popular in academia, so I learned early how to use R. I worked for a team in insurance consulting here in Seattle for a number of years that bases everything in R. So I'm very comfortable prepping data and kind of doing a lot of data munging in R. I use Python a lot to interact with DataRobot, actually, through DataRobot's API. So in this case, I used Python to essentially send API commands to the AutoML platform and get responses back quickly and essentially iterate through a coding environment where I just called AutoML in the cloud sort of as needed. And then the training time, I had 3 answers for this. If you go through the whole process I used, leveraging the DataRobot API, it was about 5 hours to train start to finish each iteration. If you just take the final models and run them in the Kaggle notebooks that I've provided, you can run them in 10 seconds. If you just take the hyperparameters out and run the elastic nets, of course, an elastic net on even 60,000 observations doesn't take very many seconds to fit. Or if you were to want to retrain the elastic net hyperparameters, mainly the penalization parameter lambda, it might take about 5 minutes to run a cross-validation and train that. So it sort of depends on what part of the process you jump into and what tools you want to use. But those are kind of the training times here. We all pause. I don't know, Addison, if you have a question.
No, that's all great so far.
Cool. Let's talk about some feature selection engineering. I'd say, like, if I had an overarching goal to how to capture information from college basketball data, what I wanted to figure out is, A, is there a common strength I can derive from this team for this season, or for each team from this season? But then 2, is there something that they've done recently leading up to the tournament that might have a little more signal, like when teams start to turn things around? Ideally, and this is one thing I've done for soccer, I would have wanted to actually have some sort of player metrics that I could aggregate up to the team level. And with those kinds of metrics, what you can do is you can actually pull players out of the starting lineup who get injured. So like, this is going way back for some people, but when Cincinnati about 20 some years ago lost Kenyon Martin going to the tournament, Cincinnati was a 2 seed, one of the best teams in college basketball. Without Kenyon Martin, they were garbage, and everyone knew it, right? And if you had a model where you could just pull a player's kind of performance out and put a replacement player's performance in, you could easily adjust as the tournament starts to things like that. I didn't make it that far, but if I tried to measure sort of like a team's, recent trends and see if that was important. So
yeah, in previous years, we used to have a partnership with the NCAA that gave us a little bit more granular data. But frankly, there's a disparity in the way data is collected between the men's and women's tournaments. And this year we decided to merge them both together. But we used to have some player-specific data for the men's tournaments. It's also a little bit, we acknowledge, a little bit tricky, where for the sake of the competition being feasible to run on our side, we have to do a pretty much a one-shot prediction before the tournament even begins.
Yep.
And that doesn't allow you to have a dynamically updating prediction model based off of if a player got injured in the play-in games, much less, or even the reverse. It could be, are you seeing a player heat up arguably throughout the tournament, even though I saw some reports that's not even really something that actually is true. There's no such thing as being on fire. But anyway, yeah, so it's a very interesting way of how you might have done it differently if there was different sets of data and if you had the opportunity to adjust your model as new information was being provided.
Absolutely. That actually segues, though we talked about conference effects a little bit, but also thinking about if you had individual player effects, how you might use them. And the way that I'd used them in the past and the way that I used conference effects was I actually used them as offsets. And so like in machine learning, an offset is basically like feeding the model a starting point, like a seeding it with an idea. And the idea here is actually a set of predictions. It's like a first round set of predictions that the model can then learn to build around. The power of this is that machine learning algorithms will always run some sort of a regularization regression approach that pulls weak information back toward a common mean, basically, right? Like if you're trying to predict for a team that's only played 5 games this season and you don't have no other information other than those 5 games, you're going to heavily regress your predictions back towards some common average until you get more information. So what I wanted to do is seed my models with like a different intercept, basically, a different starting point. And that starting point in this case was the conference effects that I derived from the non-conference schedule, which typically happens in the first month of the season. Because I wanted to train on later in the season on the games that actually are like March Madness or exactly like March Madness games, right? Or the NCAA tournament games. So what I did here is I used conference effects as offsets, but just conceptually, you could use, if you had player information that you were aggregating up to a team level, and that information might have come from information about the players in high school and their prior college years, you could pretty easily feed that in and get decent predictions for the first game of every season. And now you can train a model on the whole season or on multiple seasons to understand how player effects predict team outcomes. And you can use those offsets now to just on the NCAA tournament or just on the last month of the season or something like that. And you're essentially infusing your basketball knowledge, data science knowledge, whatever, and setting it as an offset, right? Setting it as an intercept. You can think about it that way. So I've used this trick in a few different ways. Some for using player effects at the team level, and in this case, using conference effects. So derive the conference effects from months 1 and 2 of the year. And I have like actually a little chart of the women's to show in a bit, but then use those as offsets in the model to train on the tournament and other March games. Some other key feature engineering that's important, especially with elastic nets, is missing value imputation and standardization. Elastic nets have no natural way to treat missing values. So essentially this imputation method was impute the missing values with the median value. And then once you've imputed with the median value, the standardization will subtract the median and divide by the standard deviation. That's the standardization approach. Standardization, very important in elastic nets because the penalization happens on the coefficients. And of course, coefficients are multiplied by the covariates, the x's. And if one x is like really big, like country's GDP, and another x is really tiny, like a percentage effect of something, then the coefficient on the GDP is going to be really small, and the coefficient on the percentage is going to be really big, just by the nature of the x values themselves. So you want to try to normalize all of your features so that all the coefficients that are being generated and derived can be penalized fairly, you might say. So those are important steps in elastic nets. For feature selection, this time-aware feature engineering that I didn't talk about too much yet at the top here, this generated something like 4,000 features. And if you think about how do you get to 4,000 features, well, it's all the different types of metrics that a team might produce. Their offensive rebounding for, offensive rebounding against, defensive rebounding for and against, points scored for and against, and all those differentials. And then I was looking back 2 weeks, 1 month, 3 months, and 6 months, basically the whole season, to try to figure out which time window matters, right? Or which time window gives you enough signal to make a good prediction. So feature selection became important because I started with 4,000 and whittled it down to, I think the women's model had 53 or something like that, and the men's model maybe had 100 or 150.
And when you said you were trying to figure out which time window was mattered the most, were you using that off of 2021 data? Were you using that like what were you using as a part of your cross-validation strategy to get a better sense of what might predict the 2023 tournament?
Yeah, no, that's a good question. So I'll kind of tell you what my setup was. The feature engineering was done on rolling windows, right? So if I was training on a game in February of 1999, for example, then it would have looked at how the teams have done in the 2 weeks, 1 month, 3 months, 6 months prior to February 5th, 1999. So that's how the features were generated. Then I used my validation approach was a final holdout set was everything after, and I think I picked like March 5th every year. That was actually a parameter that I tested, but I think it was March 5th. That basically gave me conference tournament games, NIT, and NCAA tournament games, essentially. And that became the holdout for like the final test. And then I did just a random cross-validation inside of the rest of the season, right? I think tenfold cross-validation, I think. Tried to pick a balance between getting enough training data in each fold versus it taking, the whole week to run the models.
Right.
And so that was the structure of the feature engineering and then the partitioning. The feature selection then was done using a feature impact rank ensembling, which if you look at the letters there, it spells fire, which is kind of a cool thing to use. And this is essentially like take all the top models that AutoML builds, maybe that you could choose top 3, top 5, top 10, whatever, and then rank the features from most impactful to least impactful using your favorite feature impact or feature importance tool, and then find the median ranks of every feature across all the models, right? And so by doing this, you end up with like maybe this feature was really impactful in an elastic net, but not so impactful in an XGBoost. You get a nice mix of the features that tended to be impactful across a wide variety of algorithms. And so that gave me these sets of features that went from 4,000 down to 1,000, 500, 300, 200, 100, and allowed me to kind of run the second step being blenders on all those different feature lists on all those different algorithms. So now I'm blending different algorithm types together, testing this anyway. Elastic Net's just won everything. That's the spoiler alert. But I'm testing all those to see like, if I mix an XGBoost with an elastic net and an SVM, all on feature lists that are kind of median, the top features for the median rank of all of them, can I get some more signal out of that? Again, spoiler, no, I couldn't in this case, but I have in other cases. So just something worth considering. So like jumping in, we just talked about variable importance or feature impact, I've called it too. This is a chart I just copied out of DataRobot here. Essentially, this type of feature impact measures what's called permutation importance. And permutation importance is like you take all of the rows in your data set for this column and basically randomize the values, resample them, right? So you've created a column that's now should have randomly worthless information, right? Because you've given Gonzaga now has, University of Portland's numbers, and Duke has, Southwestern, Eastern Texas State's numbers. And so they all should be pretty worthless. You repredict on your holdout data set or your training data set, in this case, it doesn't matter too much. And you see like basically how much worse did your loss function get when you scrambled these values. And that's a raw value that becomes like, this is how much worse. You lost 0.05 log odds, or you lost 10% R squared, whatever it is, that's how much you lost. And the amount you lost is how powerful that feature is or how impactful that feature is. It's nice because it can apply to literally any model. You can apply to a model. You can apply to, your dad or your mom sitting at the bar yelling at the TV saying you should win because you have a 99% chance to win. You could go ahead and just, take that model coming out of your parent's mouth, and you could totally use feature impact on that too. So it's very flexible, model agnostic. And so this is like an impact chart here. Let's see if I can zoom in on this a little bit. You see the top feature up there is home. I think the conference effects are probably truly the top feature, but that was an offset, and we're not measuring the impact of the offset here. But you see home there. You see right away, this is for the men's point margin model. we see offensive rebounding differential over 6 months, essentially their season-long offensive rebounding differential. One of the interesting ones I saw, number 2 here, is the free throws made differential over 1 month being pretty impactful. I kind of had this basketball sense that probably getting to the free throw line and making your free throws is something that stabilizes pretty quickly. And just all you really need to do is observe a team's last month of doing that. And you can probably get a pretty good idea if they're able to draw fouls and get to the line. And in basketball, that's important because free throws are the most efficient shot in the game. You think about most of the time you go to the free throw line, you get to take 2 shots. Most college players, men or women, shoot 70% or better. So you're talking about 1.4 points per every 2 shots, or 1.4 points per possession. No shot comes even close to that, right? College basketball, I think, averages like 1 point per possession or something like that. So you're looking at huge efficiency gains, not to mention you're putting their best players on the bench because they're in foul trouble. So it's hardly surprising to me that the free throw made differential was up here, right? A few others ones, actually, some of the information provided by Kenneth Massey. I used like what was their most recent ranking across all the different computer ranking systems, and also like medians and averages of all of them. And it picked a few out, like the Dr. Entropy one and the 7OT one. Became just 2 that happened to bubble to the top of computer ranking metrics. But let's, instead of talking about each one of these, I can jump to the women's here. One thing relatively I noticed is that the home indicator was relatively less impactful for women than for men. Probably, I mean, I think there are thousands of pages have been written about home field and home court advantage, and we could probably have a whole nother hour discussion pretty easily on why those things happen. But I think it's just always interesting to think about how home court and home field advantage impacts different leagues in different ways in different sports, right? But you see here a lot of score differential, field goals made differential are the top ones here. But you do see free throws made differential down here, also came in handy. I suspect that because for the women, we didn't have the computer rankings handy, probably the model leaned more heavily on their recent point differentials and field goal made differentials, which is probably the highest signal in terms of how good you are, is by how many points are you winning the games, right? And then a few partial dependence plots we'll get to here in a second. I did want to pull up the conference effects that I derived for the women here. I think are interesting because the partial dependence doesn't show them, and the feature impact didn't show them naturally because they were an offset, right? So I pulled them back out. I basically went and grabbed them. And you can see here for the women, the top conference in terms of basically regularized average point margin in the non-conference schedule, controlling for the conference and the teams playing and things like that, was the SEC. And LSU, like South Carolina clearly had a great season and easily could have won. LSU did win. Not surprising to see a couple big-time SEC schools go deep, right? But also, I mean, you see the Big Ten produced Iowa. I think probably an undervalued Iowa team to start the tournament. And Big 12, ACC, Pac-12, Big East, kind of a few of the major players. You'll notice, you know, we associate UConn in recent years with being a real powerhouse. But the Big East wasn't fantastic this year, and UConn actually went out early to a Big Ten school in Ohio State. So, you know, maybe there's something to be said for keeping your conference effects up to date, you know, and keeping track with which conferences are strong this year. So to step back, the way that I actually did that, I built an elastic net ahead of time where the main drivers were, okay, who's the home conference, which is the away conference, right? But also, I stole information from the future. I cheated a little bit. What was the team's in-conference margin of victory? That was controlling for how good the team was within the conference. And then the conferences, the actual indicators for conferences were telling the model which conferences were actually playing, so that I could derive conference effects while controlling for the fact that it's not always the first best that plays the first best from each conference. It might be the first that plays the worst, and you want to kind of try to control for that. So that's how I pulled what I think are fairly well-controlled conference effects out, and that's what produced charts like this for both men and women. I mentioned home court advantage. This was actually very pleasing. The yellow line here is partial dependence, and the orange and the blue are actual and predicteds. They're just being put on the same plot here. The range here of the partial dependence line is about 3.5 points. gap from home to away, which is from the literature over the years is exactly what I would have expected. So that was a very comforting thing to see is that roughly 3.5 point spread coming through there. Here also for the men, the offensive rebounding differential was a top one. You'll notice the slope is negative, and that's because this was specifically the offensive rebounding differential for the away team. So when the two teams come into play today, how has the away team done in the last 2 weeks? In this case, I think it was actually 6 months, so the whole season. But of course, the better the away team is, the worse the home team's predicted margin will be, or predicted win probability. So that's why the slope is negative here. I think I have some women's ones here too. So this is free throws made differential for the women. One thing I did for all of these box score statistics is I normalized them per 67 possessions per game. Teams like Iowa women play really fast, lots of possessions. Basically any men's team in the Big Ten, really slow, grind it out, right? So I wanted to control for that. So it wasn't just like, this team scored a lot of points. It was this team scored a lot of points per possession is what I wanted to go for. So these are free throws made differential per possession, just to kind of clarify that. But this is the home team. If the home team has a better free throws made differential, they're more likely to win by more points, basically. And the range here from the lower end to the upper end is about 1 point to about 5. So that's another 4 point range, essentially, on free throws made differential, but possible from kind of the worst differentials to the best differentials. Just a flavoring of some of the metrics that came through and why I think they're important. But going back to some of these, if you're a basketball nerd, you probably read Dean Oliver a lot in the early 2000s, who was kind of a bit of a pioneer in figuring out what's important when it comes to basketball, predicting basketball outcomes. And he kind of coined the 4 factors. 4 factors being, do you shoot a high percentage? Essentially, do you get a lot of points per shot? Do you get to the free throw line and make your free throws? Do you prevent turnovers but force turnovers from the other team? And do you win the rebounding battle? And if you can do those 4 things, he was like, you'll be very good. And so if we translate this over to data science, if you can just use if you had 4 features to use, or combinations of 4 features, those would be ones to focus on. And those are ones that came through almost naturally in this feature selection process. So it warmed my heart, to be honest. Okay, training methods. I talked about this already. I used AutoML. And if you're unfamiliar with automated machine learning, it's essentially like, it's not unlike March Madness, not unlike the tournament. It's like a tournament of models. So it's like you're running on maybe a subset of your data, you're running 40 or 50 models. Maybe you're testing not only the final algorithm, but you're testing whether or not you want to standardize with the median or the mean, whether or not you want to use one-hot encoding or some other type of categorical encoding. And you're trying all these different combinations and you're throwing them at a subset of your data. And maybe the 20 or so that do best elevate to the next round, and you fit on a bigger subset of data. And then you kind of elevate to the next round until, I think the way that Data Robot works is by round 4, they pick one for you. Like, this is the one that kind of came through the tournament. So definitely that was, I leaned on that. I leaned on the FIRE method I talked before, and I leaned on blending top models together, even though, again, it ended up just being individual elastic nets or blended elastic nets in the end. But I think one of the most powerful things that I did that at least helped me was creating these power rankings, which you see off to the right. This was how I iterated really quickly, so that when I would do a run overnight, I would call the API and make sure to get the predictions back at the end of the run and put them into a power rankings kind of thing. And the power rankings are nothing more than using the Kaggle submission, which was predict the outcome of every possible game that could be played, and then just measuring how each team would do in a hypothetical home and away season where they just played every game twice. So I flipped the prediction data set on its head. And so every team that was home at the original became team 2 or became the away team, and flipped them around, right? Predicted every team for what ended up being like a 720 game season or something like that. Calculate their average win probability in this case, or their average point differential. And you end up getting these power rankings, which I think were very powerful, because I brought up South Dakota State women earlier. They were number 2 for the women over here after like iteration 1 or 2. And I was like, okay, this thing's broken. Like, I know they had a great season in the Summit League, but they're not the second best team in college basketball. And so that was what got me to try conference effects. That's what got me playing around with that. But I was able to pretty quickly iterate just about 3 times, just looking at charts like this to make sure that I was getting roughly what I expected to get, but also that the surprises that were there were either I could explain them or I could find a trick that I would try in the next iteration. I'm pretty sure it was Bill James, the baseball analyst, who said, and I'm going to totally paraphrase this and probably butcher it. He said something effective: if you build a model and it agrees with you every time, it's a worthless model. And if you build a model and it never agrees with you, it's probably wrong. If you build a model and it agrees with you like 80% of the time and it surprises you 20% of the time, you probably have something valuable on your hands, right? And that's a rule of thumb I like to use with something like this. It's like the surprise here on this side was almost certainly Connecticut, maybe Tennessee. Connecticut is a 4 seed. I think they're both as 4 seeds, if I recall correctly. But for the most part, you see all the 1 seeds are represented here and most of the 2s, right? So we're doing pretty well. Same thing in the women. LSU is the highest 3 seed here. But mostly you've got a 1 seed. Stanford was a 1 seed. Virginia Tech was 1 seed. I think Indiana had the other 1 seed. So you've got all the 1 seeds, all the 2 seeds. The surprise there is the 3 seed bubbling up to the 2 line. But this is how I kind of iterated. I'd have basically this waiting for me on my computer screen in the morning so that I could say, am I ready to submit or do I want to try something new?
So if I can stop you here just a little bit,
Sure.
I think you mentioned this idea of sort of surprising you, but also you don't want to be so far off that you're saying this doesn't make sense. On the women's side, we know South Carolina and LSU, as basketball fans, and even Iowa, probably the 3 big. Well, at least South Carolina and Iowa for sure. Iowa with the Caitlin Clark effect, South Carolina having the current dynasty. That seems to check out. We go over to the men's side, though. Connecticut, obviously the right pick to be as high as it was, but was pretty underranked. Arguably, they were being ranked in the top 20, not the top 2.
Right.
Purdue, your model ranked a lot lower, and in fact, they became the 2nd team ever to lose in the first round as a 1 seed. At what point do you find yourself saying something's off here? I don't think that Purdue should be ranked this low or Connecticut this high, versus, like you said, that, well, my model probably, I know my model is uncovering data that my intuition isn't.
Yeah.
How do you sort of balance that?
So totally great question. With Connecticut, I was definitely surprised. And here's what I did with Connecticut. I did dig into Connecticut, right? Because I was like, okay, if I'm going to say a 4 seed is my 2nd best team, I got to be able to justify that before I submit this, right? Connecticut had by far the best point differential in conference season, especially the last roughly 3 to 4 weeks, maybe even 6 weeks. I did all the numbers, and I'll shoot from the hip here, but it's something like over the last 12 games, Connecticut averaged like a plus 13 point differential. And the top team in the Big East, Marquette, was like plus 9. Creighton was like plus 8. So Connecticut started blowing away their own conference, well before the tournament started. And I think the model picked up on that. The like something like Shapley values I used, and it was definitely picking up on like, yeah, Connecticut is blowing away their opponents right now. So it found something there. The Big East was certainly not a bad conference. It's considered a Power 5 or Power 6. And so they weren't getting hurt massively on their conference, any sort of conference effect. And the last thing I looked at, betting lines, were liking them at the time I was filling this out. Looking at futures lines for the tournament, they weren't, as a 4 seed, you'd expect them to be somewhere between the 13th and 16th best odds to win the tournament. And they were well inside the top 10. They weren't number 2, but I think they were like 8 or 9 or something. So they were a wide variety of things were pointing at this being a team that was better than a 4 seed. So that got me comfortable with Connecticut. Kentucky, actually, same way. They were a 6 seed, so you would expect them to be more on like I guess what that'd be like 21 through 24 line. Here they're up at 10, but they were actually favored to make it into the Sweet 16 over Creighton, and in the kind of the futures odds and the betting lines, and also had a good season in the SEC. So I was able to kind of get comfortable with those using betting lines and just looking at the prediction explanations from the model, right? Purdue did seem low to me, but also like they felt, and I hate saying this as a data scientist, they felt like an underwhelming 1 seed the whole year. It was almost like they were always on the one line because no one else wanted to win basketball games. And they were just like, well, here we are. We're still winning basketball games in the Big Ten. And they were really reliant on a single player, basically, right? Zach Edey, I watched a game when they played Michigan State earlier in the year, and I swear they gave him the ball every time down the court. And if that guy gets in foul trouble, or if that guy's not on that day, how do you make up for that, right? How do you go to in that case? So I had some gut feelings that Purdue wasn't really a 1 seed. The betting lines, I think, had them as the lowest winning margin in the first round of all 1 seeds. You tend to see 1 seeds about plus 20 or better, or, favored by 20 or better. And they were, I think, only like 15, which is still, they should have won, but it's significantly lower than your typical 1 seed in the first round. Excuse me. But yeah, that's kind of my process. I look at things like that. When something stands out, I go and dig in and say, is this something that's believable? Can I justify this? And so by about iteration 3 or 4, I was happy with this. And at that time, it was also probably midnight on like March 16th. And my human alarm clocks were going to wake me up in about 6 or 7 hours. So I was like, okay, we're going to submit this right now. But yeah, I guess the last couple of slides here, a couple interesting findings. I mentioned there were like the 5 little tricks to almost win a March Mania Kaggle competition. These are the 5 that I picked out as kind of being, I think, the differentiators. Again, we could run this next year. I could run the same model and be 202nd or 1002nd, right? I think 126 games of 20-year-olds competing is going to throw wrenches everywhere most years. But I think in general, these make sense, just kind of like over time. I think these will work well. The conference effects, which I talked about, I think anything you do to control for strength of schedule is valuable. And I used conferences. I think there's a number of ways you could do that. One thing I haven't talked about yet is using multiple models and point margin smoothing, which I'll actually jump down to this slide and talk about it. I ended up building men's and women's models separately, but also built a point margin predictor model and a win probability predictor model separately. And the reason I did that is because, for the submission, I had to give win probabilities. But I think that point margins are much more stable and more indicative of good teams. And so I wanted the model to be able to learn from, 20-point wins being different than 1-point wins. And so like, you think Iowa, for example, is a team that scores a lot of points. They get out and run. They often win by a lot of points. And I was noticing that at the first iteration, their win probabilities in that evaluation setup that I was just showing on the last slide were pretty low. They weren't like a top 5 like you saw there. They were more like out of the top 10. And then when I looked at their point margins, their predicted point margins were like 5th best, like where you saw them. And so teams like that were making me think, probably I need to pay more attention to the models that are built on point margins, even though I have to submit the win probabilities. So here, this is just a plot of all the games. I think this is all 131,000, or maybe it's just men. I don't remember exactly. But it's all the predicted win margins on the x-axis, the point differentials, and all of the predicted win probabilities on the y-axis. And you actually see a fair amount of vertical spread here on any vertical line, indicating that for a particular win margin, the win probabilities can have a pretty varied values. And this was just my gut saying, I want to build a model that's more founded on win margins, point differentials. And so I ran a regression that predicted the log odds of the predicted win probability using the predicted win margin, just to smooth out, I call it smoothing out, the win probabilities to have them being based on win margins. And I think that probably helped a lot. The teams that helped, I noticed, were Iowa being one. And I think, I can't remember on the men's side, but there was another team on the men's side I noticed that made some gains because of this, and it made sense. Like I liked that happened. I talked about the training window. I opted to use some regular season and tournament. Some of this came from my soccer background. I've been trying to predict Major League Soccer outcomes off and on over the years. And if you go back 10 years, Major League Soccer has only produced about 3,000 or 4,000 games. And I've really struggled to get signal out of anything that wasn't a major driver. So the models end up being very simple. And I thought, well, if I only train on tournament games, I'm only going to have about 2,500 men's games and maybe 1,500 women's games or something like that. I want more games. I want the model to be able to learn things like the 4 factors of basketball. So I chose the training window to extend back to February, and then used a home neutral kind of indicator for handling how the neutral site games would be different than the true home court games. The partitioning method, using late March and essentially the tournament as the holdout, When I chose top models off the leaderboard at the end, I actually did a weighted average where I took 50% of the holdout score and 50% of the cross-validation score, even though the holdout only made up about 5% of the total data, because I wanted to, in the end, weight toward models that were doing better during the tournament, even if I wasn't fully training on those models. And then, like I showed, being able to evaluate quickly with the power rankings, take a look at the power rankings and figure out how can I change in the next iteration to do better. So those are the top 5 things I probably did that I think not only helped in this tournament, but could probably help year over year. Excuse me. And then I think the last one is just how do you build the simple model? Stepping back from this slide for a minute, I think probably if you focus on the 4 factors of basketball, that's the simple model. Build a model on your points per shot, basically points per field goal attempt, your free throws made maybe per possession or something like that, your offensive and defensive rebounding, and what you allow the other team to get for all of these, and then your turnover differential. Do you turn it over more than your opponents, or are you good at protecting the ball? These are all fundamental to being an efficient basketball team. And I think sticking with like versions of those 4, you'll probably do pretty well. When I actually ran these top algorithms on different subsets here, I started with about roughly a 30% R squared, and I lost about 10% when I went to 25 or 50 features. So I could get about 90% of the way there with 25 or 50 features. And I think this is men's now I think about it, but the full 300 some odd variables for men did produce that slightly better R squared value. And Elastic Nets did all the heavy lifting. The picture here is a data robot blueprint for one of the models. Essentially just talks about how categorical and numeric features are handled, how for this particular Elastic Net, it uses 2 different standardization techniques, Reddit transform and the median standardization, before feeding the final features into the ridge regressor. Yeah. So I think that concludes the things that I had on my mind.
Fantastic. Yeah. Really wonderful to hear and walk through that. Really kind of cool to see the blend of machine learning and what would be or traditional machine learning, as you may call it, and intuitive basketball knowledge, and how sometimes those aren't always, or often they are in sync. It's not that machines are really just supporting what we've known for a while, but in a much more nuanced way. On this competition specifically, I know in the past, this is the first that we've used the Brier score as an evaluation metric. We historically used log loss, and we found a bit of a gamification of people doing some clipping of their results. Did you do any post-processing with your predictions?
I had the submission that took second here was straight up, just exactly what the model said after the process I described. I tried a post-processing for submission 2 where I think I just randomly took 2 women's games that had close to 50% probabilities and set them both to 100%, thinking that if I hit both, it would be like winning the lottery on a 25% probability. I would gain a lot of points by doing that, and they both lost. So that ended up being much lower. What I did realize afterwards, though, is if I had just picked one such game, a 50% game, and had one of my submissions picked for one team to win and one picked the other team to win, that would have been enough gains on the one that got it right to move into first.
Yeah.
So, hindsight's 2020, but that was the limit of the gamification.
We've seen that in the past, but if you only have a limited number of submissions, once you get past picking one game, you have to pick the one that you want to try to risk it all on.
Yeah.
As the tournament unfolded, were you surprised? Like, I imagine you're probably going back and looking at how your model was performing as it was going on. Were there any features that you found were standing out more so in this tournament relative to historical performance? Like what was free throws, or number of free throw attempts, for example, significantly more important this year than it was in previous years?
That's an interesting. You know what I didn't do is I didn't go over the actual games that happened in the tournament to see if there was commonality in the teams winning, or if my model, here's one way I might do it actually, now that you're mentioning, is derive Shapley values or prediction explanations or whatever for the actual outcomes for the games that happened, and then look at the teams that won and look for what are the highest Shapley values or the highest prediction explainers for those winners. You know, I think that could be really interesting. I didn't actually do that. But you've probably given me homework.
Yeah, I'd say like as a basketball fan, you know, obviously we've seen the NBA, the transformation of the game towards more 3-pointers and just being a different type of game. With that, I wonder if you weight, this is me speculating, if there should be a certain weighting towards features that grew in importance closer to the current season, and that if, for example, free throws were way more important in 2022 than they were in 1999. Or something, or as we've seen the average height of collegiate basketball players growing, does that mean that rebounds become actually less important because people can rebound or something like that? Just speculating. I wasn't sure if that was something you had considered.
The one thing I did notice is, like, you know, the Pac-12/Pac-10 hasn't really been a powerhouse for years, maybe even since the late 90s, you could argue. And as I was digging into some of this stuff, I noticed that the Pac-12/10 has produced some of the worst 3-point shooting teams over the last 10 years. I think I looked back to 2015. They're the worst of the power conferences and like the 4th worst out of 30 some conferences, right? Wow. And they haven't done particularly well. And it could just be a lot of correlation there and not causation. But I do think that, you know, as teams accept the high efficiency game, which is get to the free throw line, hit your corner threes. NBA, it's corner threes because they're shorter, but hit your threes, get to the free throw line. Conferences that have accepted that, you know, are continuing to do well. And I think the Pac-12 may have been left behind a little bit there.
Yeah, I was just curious as you were as you mentioned, putting some different time benchmarks, or that's not the right term, but rather some timing thresholds at which you were analyzing different features, if you consider doing that across seasons as well as within intra-season. You mentioned earlier too, you know, preferring to have, or it would be nice to have individual player data that you could toggle a bit more. What would be some other data sets that you would speculate might be valuable, or you'd be interested in playing around with in future competitions?
The player one was the only one I thought of as I was modeling. Like if I said, what's the one thing I would do differently if I wanted to go beat Vegas, right, or something like that, is it would have individual player values. And that would mean not just what the players produce, like points per game, because at the individual level, that's not particularly helpful. Some sort of evaluation metric, like value over replacement player, which is more common in the professional leagues. But I do know that there do exist some metrics. I think one is called like a box score regularized plus minus, which essentially takes player combinations that were on the court at different times, creates indicators or, you know, intercepts essentially for every player, whether they're on the court or not, and then measures the output of the score line essentially when they were on the court, controlling for all other 9 players that were playing at that time. And with regularization, you could get reasonable estimates for players that have any sort of a sample size as to how valuable they are. And then you'd leverage those going forward as you can aggregate those individual player regularized plus minus scores up to the team level, maybe weight it by starters versus, you know, bench players. Probably have some rules about if a player hasn't played very much and they're not starting, regress them back to some level. That was where my mind went for this tournament for like next phase. Another one I thought of as we're going through is I thought about pulling in like geolocation data, right? Like essentially get the latitude, longitude of all of the arenas, the home arenas, and then where the games were played, and measure home team's distance to arena, away team's distance to arena, differential, and try to figure out if during the regular season, learning things like that could help in the neutral site tournament games at all, or if it's just too different, you know? Yeah,
it could be interesting. I know there's some theories on player fatigue in traveling long distances, or as well as fan travels, which like fan base could travel well to a away or neutral site.
I wonder if we could get like, you know, how much sport booster money, you know, goes into each team, and like that may be some sort of a proxy for their fan base and following, you know?
Yeah. Or even too, I guess you could think about it of like regional schools versus, you know, if Ohio State is somehow a 15 seed, they're still going to fill up half the arena. And even if it's the game being played as far away as possible as it could be.
Oh, because like 1 billion people have graduated from the Ohio State University.
Right, from the Ohio State. So you mentioned this is your first Kaggle competition. I'm curious a bit more about, had you heard of Kaggle before? What drew you specifically to this one? Are there other competition types that interest you that you are playing around with in the future? It kind of walk me through that experience of participating for the first time.
So probably about 8 years ago, I was part of at my old job, I was part of a lunch and learn thing where we would just talk about, the Kaggle competition of the month or whatever, and just hypothesize, sometimes pull our computers out and work on something, but I never got so far as to submit. And I always thought this would be really fun. Not coincidentally, about that time, we had our first child, and free time, started to go out the window. And so as I was just getting into this idea of data science competitions, I sort of had to say, okay, maybe I don't have time for that. I spend a lot of my free time working on the soccer analytics website and doing soccer stuff. So that kind of was my sports outlet for the last 7 or 8 years, or data, you could say general data science outlet. I want to do more. It's very fun. I was honestly very surprised to see my name I didn't check for the first couple of rounds. And then I cruised over to look, and I think at the time I was maybe in 5th or something. And I was like, whoa, that's a bit of a surprise, but it's fun. I don't know, the leaderboard makes it fun. There's a little bit of competitiveness to it, like sports, and there's a scoreboard. Add a scoreboard to anything and I'm in.
Right. So. Yeah. That's hence the success of things like Peloton.
Right.
That just, puts the numbers metrics on it. I'm curious. So I know you work for DataRobot. Obviously, this is part of your day job as well. How much time did you spend drawing from your professional background versus poking around in previous Kaggle competitions and previous notebooks and sort of seeing what the rest of the community was sharing? Kind of walk me through what, if any, a time you spent kind of seeing what the community was putting together on the whole, compared to, I do this in my day job. I'm fortunate to be able to use this particular technology to kind of help things out a little bit. What was that process sort of like for you?
So not because I didn't want to, I didn't have the chance to dig in too much to the community, its ideas. I didn't look at past years or anything like that. Again, I think there's a lot of good stuff there. And the only reason I was able to see something like that is on an internal Slack channel, some of my buddies at work were also entered in the competition. And so we ended up talking about some of the ideas, like the radar ranking system that has been popular in the past. And that got me to thinking about ideas. And I think I would really enjoy going back to the communities a lot. I was kind of on a timeline. And so I think where my work experience helped was I just prioritized the tasks I needed to do, created a pipeline that I knew I could iterate on quickly, the types of things I have to do for work because of time commitment, time stress there. And I think just kind of making sure that I was able to create a deliverable in the set amount of time that I had, which was, between 9 p.m. and midnight, a few nights the week before. Those kinds of skills became really useful from work, right? Essentially time management, getting something out in the time that you have, not overdoing it, knowing what I can and can't do in that amount of time. And then just building the pipeline itself, just the coding background, kind of knowing how to build organized code that I can run start to finish and iterate on quickly. I think that's very valuable. I keep saying iteration over and over again. I think that's the biggest thing because I iterated 3 or 4 times and every iteration looked better than the last. And if you can speed up that iteration cycle, you can get to the right answers or, better answers more quickly, I think. And I sort of had to do that.
And I think we found that's why Kaggle competitions on the whole, outside of this one having obviously a different format of the submit and then wait and see, but other Kaggle competitions that have a ground truth established, by getting a score back right away, it creates an iterative feedback loop that people just love and kind of get addicted to. My last question is totally selfish, which is I happen to go to a small liberal arts school called Furman University, who had an appearance for the first time in 40 years, happened to have the first upset of the tournament. Did your model give us any credit?
You know what? I will send that over. I don't have it up now, but I can tell you how well Furman would be expected to do against all the other 361 Division I schools.
Very good. And lastly, any questions for us?
Not off the top of my head. I just say thank you again. This was very fun to get back into it again after my hiatus, and I'm hoping to do more competitions in the future. But yeah, no, I love it. I love the community seems great too.
Yeah, we're always excited. I know I mentioned before we even started recording this, we love seeing not just these types of presentations, but always blown away by the way the community not just is collaborative, but sort of adds to whatever that extra step change is in the state of the art. It's not uncommon just for simply by seeing a discussion forum get started that you'll see truly the rising tide that lifts all ships in a machine learning problem and understanding what the art of the possible is for this particular problem space. So it is really great.
It's such a cool idea, yeah, and just the concept of bringing all those ideas together. I'm all for it.
Yeah, I
like to socialize the sports analysis that I do too. You know, like make it open source. It I guess maybe is a better word. Like I love the open sourcing of ideas.
Yeah, well, you know, maybe we'll have to see you, and we have some other sports-based competitions typically on the site. I think you joined just after our NFL-based competitions concluded, but hopefully we'll see your face on other leaderboards to come.
I hope so too.
Well, once again, congratulations. Thanks so much for the time today. I really hope a lot of people are able to learn well from it, and just really excited to see the work that you've done and how it will contribute to data science and sports analytics and college basketball fans everywhere.
Yeah, thanks again, Ad. Thanks again to you and your whole team.
Thanks.
Have a good one.